Okay, our final team before lunch is team number 8, which is actually a team that built a test chamber for self-cleaning solar panels. The customer is Professor Malay Mazumder from BU. So here is team 8, and I would suggest that while you're looking at all of the projects, you'll notice that team 8 has made extensive use of my little machine shop.
There we go.
Just do it.
All right, good morning, everyone. We are Team 8, the Solar Engineers, and we're working on the self-cleaning solar panel test chamber for Professor Malay Mazumder. Let's do this. I'm Christopher Petrik. These are my teammates, Sarah Griesse-Nascimento, Alex Chan, Naufal Veqar, and Kshitiz Kohli. And as I mentioned, we're working for Professor Mazumder. Now, our project is actually part of a larger project that Professor Mazumder is working on with a team of graduate students that is going to create a self-cleaning system for solar panels. I'm going to talk a little bit about that first so you kind of get an idea where our project is coming from. And the motivations for their project is that the most ideal locations for large solar arrays to gather power are located in arid and semi-arid conditions, mostly like desert environments. And in these areas, dust deposition can create a large problem. It can actually cause a drop in output of up to 30% of any given solar panel if it's allowed to go unchecked. And what they're proposing is an electrodynamic screen that would use an alternating electric current to basically clean the panels off using an electric field. And this has the benefit of not using any moving parts, water, chemical sprays. It's low maintenance. It doesn't require any additional manpower. And it basically provides an elegant automatic solution to the dust issue that these arrays would face in desert conditions. The issue, though, is that the EDS cannot be run at all times, because that would essentially defeat the purpose by sapping the same amount of power that it would save by cleaning off the dust. So what they need is a mechanism that they can use to determine when to activate it. This would be based on 2 factors, both the presence of dust on the panel and a loss of output. This ensures that you don't, say you detect dust and it's nighttime and there's no loss in power, you don't waste energy cleaning off the dust when it's not actually creating a problem. Or if a cloud passes by and there's no dust, it doesn't say, oh, there's a drop in power, we need to run the EDS and there's no dust. Once both of those keys are present, it would activate the EDS and clean the panel. And this is where our project comes in. So our task was to design and build a test chamber to simulate the desert conditions that the EDS would be operating in, detect the presence of dust on the solar panel being tested, and detect the loss of output so that we could test for these flags, determine when to activate the EDS, and then allow our customer to continue doing testing according to their needs. So the chamber itself is a 2 by 2 by 2 foot cube constructed of plexiglass. We use 1/4 inch thick walls secured with epoxy and aluminum angle brackets for additional security. A removable lid with the LED array attached to that, and a door on the front to allow access to all the equipment, components, and testing setup. So if you look over here, we have the heater and humidifier attached to the walls of the chamber with the sensors for that mounted on the side of the stand. The motor and thermocouple for the surface temperature of the solar panel are also attached right here on the right side. And then right in the center here is where everything kind of comes together around the platform. The solar panel would be mounted right here on this plexiglass mount and then attached to the voltage detector so we can detect the drop in output. And then up here we have the optical detecting system, which detects the presence of dust on the panel. And although you can't see it, the tube for the actual dust dispenser is mounted right behind this scope. So the dust will be deposited right here, and we can conduct any testing that we need to do. So this is our full functional block diagram, just showing how everything interacts. You have the heater, humidity systems kind of just providing conditions to the chamber, the dust dispenser inputting dust to the platform, and then the optics and voltage systems operating on the platform to run those tests. And then all of this data is output to a laptop and then consolidated to the user in the form of a graphical user interface that we've also designed. And now, Naufal is going to talk to you about the heat and humidity sensors.
All right, thank you. As Chris talked to you about the fact that these solar panels are found in arid and semi-arid regions where usually the temperatures can go as high as 125 degrees Fahrenheit to 130 degrees Fahrenheit, which is touching 50 degrees Celsius or even more in some extreme cases. So in those extreme conditions, that's basically what we want to test, that how heat and also humidity affects the output of the solar panel, and henceforth is going to affect the threshold for the activation of the EDS. So our current chamber is going to sorry about that. So our current chamber is going to enable our customer to be able to study the degradation effects of temperature and humidity, and also how that is going to affect the surface temperature of the solar panel. And obviously this is in light of the broader part of the project, which is to determine the threshold where the EDS is going to be activated. So the use was to vary the temperature inside the chamber from approximately 25 degrees Celsius to 50 degrees Celsius, and also the humidity from 40% to 90%. For that purpose, we installed a heater and a humidifier into the chamber, as Chris pointed out to. And lastly, our job was to make sure that we were able to gather data from the chamber and then display it onto the computer. I have a couple of pictures here of the heater and the humidifier that we've used inside the chamber. And to detect the temperature, which is obviously as important, we've used the RHT03 sensor, which we have interfaced with the Arduino Uno microprocessor in order to detect the humidity and the temperature inside the chamber. Another very important system in our chamber is obviously the dust dispensing system. As I pointed out earlier, really the dust is what is going to cause the solar panel to lose output, and that is precisely why there is going to be an EDS screen in order to clean that off. So the functionality is that we're going to have a dust deposition system that we have a dust deposition system that fluidizes the dust within the chamber and then deposits the dust onto the solar panel. The idea was to have an air pump connected to an acrylic tube, as you can see in this diagram, and then through a PVC tube that is connected to the chamber. And as Chris again pointed out to earlier, the tube is connected on top of the solar panel so that we can ensure proper and even distribution of dust on top of the solar panel. Here we have a picture of how this is going to work. The dust deposition filter tube or the acrylic tube is mounted outside the chamber. We have porous discs inside the chamber to maintain airflow, and then we have the corks to seal the acrylic tube to be able to maintain the pressure inside, and and then the tube goes inside the chamber. Also, as you notice, we have a needle valve here, which enables us to change the rate of dust deposition inside the chamber. I'm going to pass it on to Alex now.
So for our system, we have a surface temperature system, which we use a K-type thermocouple, since it wouldn't interfere with our optical system, which is used for measuring efficiency later in our chamber. But using the thermocouple required us to use a K thermocouple to digital converter, so the computer will be able to read the data. But measuring the surface temperature is important for determining the power output, because temperature, since measuring surface temperature would help us to determine the temperature of the solar panel, which is one of the important factors of efficiency for solar panels. Along with that, we also have a solar panel positioning system, which consists of a stepper motor that's powered by a motor shield. The solar positioning system adjusts the angle according to the user's desired current and desired input, and it is used to simulate the various angles of incidence of solar radiation on solar panels, which is also another important factor in determining the efficiency of it. And we also, to determine the actual power efficiency, we also measure the voltage of the solar panel, because for current of the solar panel, it is a function of the irradiance of the sun, because for the irradiance, because it is a function of receiving as photons from the sun to produce the current. And doing that, if that is like constant, if the irradiance is constant, then the factor that would only be measured is the voltage. And from VI curves of the solar panel and previous studies, the voltage is affected by the temperature. So as the as the temperature increases, the voltage actually decreases for the solar panel production. And this idea is similar to maximum power point tracking, which is used by solar power plants today, in which they measure the voltage output to determine the maximum power output that the solar panels can produce. And as you can see, at a certain point, since temperature is too hot, because of the voltage increase, it actually will decrease the power produced by the solar panel.
So this is a 3D sketch of our optical system. The LED panel, the light radiation emitted from this LED panel optically mimics the white light at about 5500 Kelvin. We have a laser module right here with the lens fitted at its mouth that allows us to diffuse the laser beam and increase the spot size. The idea is that dust present on the glass surface would cause the incident laser beam to scatter, and then it's made to, and the reflected light is made to pass through a series of filters, first a UV and IR blocking filter, then a dichroic flame red filter, and ultimately only the laser light is allowed to reach the detector. For our detector, we have used Texas Advanced Optoelectronic System TSL230R, frequent light to frequency converter. There are two main reasons why it made it necessary for us to diffuse our laser beam. The first being that very few and tiny specks of dust present in the air or on the solar panel or the glass surface can cause a coherent beam of light to scatter at wider angles, and it would give us inaccurate results. And secondly, as it can be seen in the picture, that the photoreceptor array on this chip is really tiny, and aligning the laser and making sure that that coherent beam hits it would have been a near impossible task. So this is an actual picture of our optics and voltage system. This is how it looks mounted in our chamber. So this little thing right here is our laser pointer, and the lens is also fitted right at its mouth. And here's the platform that houses the solar panel, and this filter scope tube holds the IR and UV filter and the dichroic filter in it. And at the end of the tube there is like a detector tower right here. The mounting is such that these little things can be moved up and down about this vertical post, and also moved around about the vertical axis. And this system is present on either side that allows us, that gives us all the degrees of freedom and makes it very easy to align the laser with the detector. And here we have the voltage being measured right here. Now, talking in a little bit detail about the filters that we have used. The way conventional filters work is that they absorb the unwanted part of the spectrum and transmit the desired portion. We have used dichroic filters. What they do is they selectively reflect the unwanted part back rather than absorbing it, and let the desired part pass through. Consequently, the light that comes out is exceedingly pure and saturated. And as it can be seen from this picture, that it's a comparison of a dichroic filter with a conventional filter. It emits a very narrow band of light. That means it's very pure and saturated, and also the transmission is as high as to 80% rather than less than 20% for a conventional filter. There were a few concerns at first that light must pass through the filter perpendicular to the coating on those filters, or there could be like slight variations in the transmitted color. We performed sufficient amount of testing to ensure that the way that our system is mounted does not affect the transmitted wavelength. And so closer look at the design. This is the light that's coming off of the solar panels. First, it's passed through a UV and IR blocking filter that prevents any wavelength of smaller than 370 nanometer to pass through, and also eliminates any infrared light. The next filter is a permacolor flame red filter that allows the laser wavelength to pass through. Another reason for having this set of filters is that our LED panel can get very bright, as high as about 22,000 lux. So we did not want that, even though it's necessary for us, the presence of the LED panel is necessary so that we can measure the voltage at like different intensities, but it should not at the same time interfere with our dust detection mechanism. So these series of filters also eliminate all the spectra of the LED panel. So the light that ultimately reaches the optical detector is the laser light, and that's exactly what we wanted. And I'm going to pass it on to Sarah.
Okay, so the final component of our project and the last thing in the way of lunch is the graphical user interface. So as you can see, this is the layout of our interface. It brings together all the components of our GUI, allowing us to see data in one specific screen, and it also allows us to control the motor. So the first thing you do when you open up the GUI is to first determine the COM ports that are being used by the Arduinos. So here's the panel for selecting those. To make it easier to determine which Arduino you're working with, we've labeled the sensors that are on each of them. The second step tends to be to calibrate the optical system. As KK mentioned, there's a laser and it has to be aligned so that the reflection goes straight into the detector. So what we've created is this calibrate optics option, which will give you real-time values of the voltage and the photon flux that we're observing, so that you can keep changing the laser and observe immediate changes in the readings. So when that happens, you get this. So it shows 20 readings, and you can keep performing the calibration until you observe a stable maximum reading at about 7 to 9,000. Then the next step would be to take measurements. So the first measurement option is the angle platform. So you can change the angle by entering the angle you would like. We have it from a range of 0 to 60 degrees. Also, for the first time, we ask you to enter the current angle, and then once the change in the motor has been done, you can see the last change, the angle change is computed, and this goes back to 0. So it allows you to know when it's done, but you can also observe it in motion. Then all of the other sensors, you can just hit the measure button, and it will display the value that was measured in these boxes. Same happens with the optical system, but you can also display a plot of a 3D graph, which can be hidden, as you saw in the first figure. And that just shows the photon flux and the voltage as a function of time. And then one of the other features we've added is if you would like to export all the data that you've measured. This includes the motor angle, the temperature, the humidity, and the surface temperature. That is all stored in a matrix, and it can be exported to Excel. And so that is helpful if you want to store any data that you obtain during one experiment. Finally, there's also the snapshot option, which is what I use to put these figures up here. You can just have an image of your results. So finally, this is our final visualization. In summary, we built a test and monitoring system to study the effects of dust on solar panels and the use of the EDS to improve the efficiency of these panels. The project is part of a bigger picture to enable the use of the EDS system on solar panels in power plants in desert and semi-arid conditions. We would like to thank our customer, Professor Mazumder, for allowing us to be part of this exciting initiative. We'd also like to thank the collaborators of this project, Professor Horenstein's lab, the Arava Institute in Israel, and Bingoa Solar. And we would also like to thank all of the senior design staff, Professor Pisano, Kia, the GTFs, Peter, Alyssa, also Jeff and Mike, and they were very helpful. And finally, we are very proud of our project, and we hope you have time to come see our demo. And that is it. We will take your questions now.
I have a question. So you have the humidity sensor. Really, the feedback loop between the what you use to put in a value for the humidity, or is it just a manual turn on?
No, it's manual.
Yeah.
I'm curious, what's the typical humidity of a desert environment?
Generally pretty low, but it can rise up to even 90% if they are getting rain in those rare occasions. So even though it is usually a fairly low value, you can have instances of higher humidity in the desert.
What's fairly low?
35%, no, so 35, it usually ranges from 25 to like 45, I want to say. But, so I just average it out at 35.
So why is so you said you designed your system for 40 to 90% humidity, so I guess you won't be able to simulate the lower humidity?
Well, that's what the customer requirement was, so we kind of did what he asked us to do. Also, when the chamber starts out, it is usually at 25 degrees or 25% to 30% humidity, and then we have to change it to whatever value you want it to be.
We don't have anything in place to actually decrease the humidity. We can only add humidity to the system, so you can't really, like, we can supply anything 40 to 90, but we can't lower it below whatever the ambient humidity is. So that's kind of where that requirement comes from, if that makes sense to you. Professor Hornstein, did you have a question? Oh, okay. Sir?
I'm sorry, this may be evident to everybody else, but not me. This is a multidisciplinary project.
It's only...
Built the desk fixture, correct?
Yes, that's correct.
Yes.
Yes, we're all electrical engineers.
Okay, that's pretty impressive.
Thank you.
Thank you.
All right, thank you.